Today I will present the In-Situ Scour Testing Device, which is ISTD for determining the soil erosion resistance in clay. While we go through the presentation, you will see some kind of geotechnical stuff. But to be honest, I'm still 80% of hydraulic engineer. I just happen to know some geotechnical soil testing and also field explorations, but I'm still more of a hydraulic engineer. This presentation will answer the following questions. So why we need the ISTD, and what is ISTD also, and how it works, and what you will get from an ISTD test. And I hope that this presentation may give Brad some tools so he can cope with the challenge of the scour analysis in cohesive soils. First of all, why ISTD is developed. Now let's zoom into Lafayette Bridge in Michigan, Bay City, Michigan. This bridge is currently classified as a scour critical bridge and is in the process of being replaced. The preliminary scour depth has been predicted to be 35 feet below the riverbed, and that including cutting into the steep to very steep clay of 23 feet. And because of the deep scour depth, there will be needed of 200 pieces of 80 feet long, very large H piles. But the number will be 18 by 204. So it's 18-inch wide and 204 pounds per foot. So it's a really large pile. In Michigan, because Michigan, usually they just use a smaller pile, which is 17 by 140 something. So these large piles require the Michigan contractors to either modify their current equipment or buy a new equipment to install the piles. So Michigan, since ISTD can help in the scour analysis, so Michigan State DOT trying to use this technology to see how the true soil erosion resistance of the clay it is. And this picture shows the bridge when it's open to allow a large vessel to passing through. And on the right, you will see this. It's really small, but you may see that. Okay, it's not working. So it's here. So this is our ISD setup for Michigan test, and if the scour depth can be predicted shorter or shallower, so that maybe a smaller or shorter each pile will be used to certify suffice the foundation design requirements, and that will save a lot. And this picture is a closer look of the overview ISD setup in Michigan. Dr. Connell Kearney yesterday has discussed about the federal highway scour depth equilibrium state design approach. And that requires the collaboration between hydraulic and geotechnical engineers. Basically, the idea is we want to separate the scour into two parts. One is the scour, the eroding power decay from the flow. The other part is the soil erosion resistance. So if both are known, while at the depth where these two will equal to each other will be the depth of your scour, and that's quite straightforward. The ISTD can measure the soil erosion resistance as a site of interest, and that allow us to test the soil erosion resistance on an undisturbed state. That means we can eliminate any disturbance due to the sampling, transportation, and also the storage of the sample. Here it shows that how, here it shows we have 3 layers of soil. And while you do the ISTD test, you will have the pink bar, which represents the soil erosion resistance for each layer. And the yellow curve is the eroding power decay from the flow. So as you can see in the first layer, the pink bar is smaller than the eroding capability of the flow. So the scour will occur. And in the second layer, of course, the eroding power will decay, will be getting smaller, but it's still larger than the soil erosion resistance of second layer, so the scour continues. And eventually it intersects with the pink bar of the third soil layer, so that will mark your equilibrium scour depth. And you can see that it is very close to the true scour depth. Next, what is ISTD? So we know that ISTD can be helpful, but what is ISTD? So ISTD is a patent device which is developed at the hydraulics lab in Turner-Fairbank, and it has some components. It has a 3D printed erosion head, sensors, and PVC pipes, which will allow the water flow to erode soil on site. Here you can see that we have water pump, generator, ISTD operation units, and closer look of the ISTD components. We have the linear drive, and we have some other parts. The one thing of this, of the most component is electric motor on the linear drive. This will allow that during the erosion process, that this electric motor will push the PVC pipe into the ground, and that descending speed of this motor will tell us how fast the erosion rate will be. Here we have a animation of the flow direction inside the erosion head. The blue shows the inflow, and the green shows the outflow. As you can see, this is a very complicated shape, and we have to use 3D printer to print this erosion head. So the ISTD testing procedure, how it works, it can be divided into 5 stages. So the first 2 stages are basically the geotechnical drilling practice. So we will require a drill rig, and the drill rig will use hollow stem auger, drive hollow stem auger into the ground to a target depth, which will be ½ feet above the target depth. And you also use pilot bait, which is this geotechnical term. So you use pilot bait to clean the hole. And the next step is we will have to clean the hole because the soil, the ½ foot of soil right below the auger will be disturbed. So we just sampling the ½ foot soil out, and then we push again with Shelby tube 1.5 feet into the ground, and that will be the soil for the ISTD test. Now, stage 3 happening on the above the ground is we will put on the linear drive and then lower the erosion head into the casing. And stage 4, you can connect in all the hoses, all the pipings, and then you can start your flow. And the picture shows in the middle, it gives you the idea how the flow recirculates through the ISTD system. Stage 5 is the whole control of the testing in the field. So the linear drive has the electric motor, and the motor is controlled by a computer program, which will lower the erosion head automatically when you have erosion happens. So the movement will always keep a constant gap between the erosion head and the soil surface, because this is very important and very critical to make sure that we have a uniform or constant flow condition. You can have different flow rates through the pump. Eventually, we'll collecting data that we'll use to develop the critical shear stress. This animation just shows all the stages until you can start the ISTD test. So this is drilling, and the next step will be pushing the Shelby tube to sample and clean the first ½ feet of soil away. And then we can push the Shelby tube again, because Shelby tube is gives you the less disturbed soil, and push 1.5 feet below the target elevation, and that's your soil will be tested inside the tube. then this is erosion head will be lowered, and a constant gap will be maintained by the electric motor during the erosion test. So this will show the data collected in one test. As you can see that we have two soil layers here. Firstly, they are both silty clay with N value different. The first layer is N equals 3, and next layer is a stronger layer. And we can run the flow rate Q1. Over the time, you will see how fast that the erosion has been pushed down. And you can fit a linear line to the data, and then the slope will be the erosion rate. Then you can see as you increase erosion, the flow rate, of course, the erosion rate will increase. Now, the ISTD, of course, is a circular device, and it will not generate a horizontal shear stress like as in the open channel flow. So we have to calibrate the flow condition, how that will be translated to an open channel flow. So we use the In-Situ Scour Testing Device, the ESTD, to do the calibration. ESTD can reproduce well-controlled open channel flow in the lab, and it can also directly measure the shear stress, which is very important in the erosion analysis. And it was used to formulate soil critical shear stress with the soil geotechnical properties. We released a report in 2015. If you are interested, the report name is Scour in Cohesive Soils. You can get more detail about this In-Situ Scour testing device. Now, the calibration involves soil erosion tests in both devices. As you can see in this picture, the ESTD will generate a erosion curve, which is erosion rate versus the shear stress. And of course, ISTD will give you the erosion rate versus flow rate in the ISTD. Now, the idea is to use the same well-controlled artificial lab-prepared soil to do the erosion test in both devices. As long as you have the same erosion rate in both devices, then the two flow conditions in these two devices will be equivalent. And that gives us a calibration curve between the ESTD shear stress versus the ISTD flow rate. And we can use that equation to convert the flow rate of ISTD into a ESTD shear stress. And after the conversion, we will have this erosion rate graph versus the shear stress. Now, we remember for the example we showed from 6 to 7 feet, we have 4 testing data. And if we plot these 4 data on this graph, and we fit in the data with a power function, and you will have A, tau C, and B, which tau C is a critical shear stress or critical water load we are looking for. And this tau C will be the pink bar that we mentioned before as a soil erosion resistance. Now, coupling with the eroding force decay of the flow at a certain depth, then you can directly to see where will be my final scour depth. Now, we're demonstrating the ISTD across 20 states. We already finished the Mississippi and Michigan test, and today we also have the third test in Ohio, which is like 30 minutes away from here. We have a field trip. If you're more than welcome to join us. Of course, we have some requirement of the size and also on the drill rig. The size requirement is we require cohesive soils, of course, and the minimum thickness of the soil layer will be 1.5 feet at least. And also soil must be below the groundwater table, and that's some requirements of the geotechnical testing because we have a slaking phenomena. The maximum N value of the soil will be 30. The drill requirements, maybe you can skip it because this is geotechnical. But of course, we need a hollow thermal auger, and also the drill rig can have to have the power to push the casing and shelby tubes. Some specification of the device, we can generate a maximum flow rate of 0.5 CFS at a depth of 60 feet. Testing depth will be maximum 60 feet. Inflow pipe will be 1.5 Schedule 40 PVC pipes. We have steel casing 3.5 ID, casing shoe will be 3.5 OD. And the curvature of the device, it can handle a gravel up to 3/4 inch. So this map shows the 20 demos we need to finish by October next year. As I mentioned, we already finished Mississippi and Michigan, and we have another 5 already been scheduled until this November. And 13 other interested states is shown here as orange. And I also would like to use this opportunity to acknowledge the whole ISTD team. First of all, we thank Dr. Cornell Curry for his continuous funding support for this project. His extraordinary vision and belief in this project has made the ISTD a reality. We also want to thank Dr. Chao Huang, the program manager in Genex Systems, and the ISTD operation team members, Timon, James, Christoph, Daniel, Otto, Mike, and Nando. And thank you very much. And also, last but not least, Veronica and Daniel from Federal Highway Research Center helping us to reach out to states and so that we can have them to facilitate our test demos. And thank you very much. Also here, we have a barcode. If you use your cell phone to take a picture either or just focus on this barcode or QR code, you will have some information about the slides of the upcoming field trip in a couple hours. Yes, so if you have an iPhone, you can just focus on the QR code, then automatically a link will show up. So you can go to the website, you will have a very similar previous slides, will give you some information about the site. If you have an Android phone, take a picture, open the photo with Google Photos, then there will be a link that also gives you some information, so you can access that. And meanwhile, we have a printout handout. When you are boarding the shuttle, you will have one, and you can read more details about this QR code. And I think we still have some time for some questions. Thank you.
Yeah, thank you for doing this wonderful technology. And my question is, it seems like a key step in doing this is you have to calibrate between QEF versus the gesture. So the question obviously is, does it vary? So every time you have to do it at different sites, or the calibrated curve is pretty much constant?
Yes. The short answer is we hope that the calibration curve will be universe. What we had, the experience we had is we had some testing near Virginia, and we have some data from field, and that's how we generate the calibration equation. And we also go through a more detailed calibration procedure, which we use the soil, which is artificial soil prepared in the lab. So we have better control. We can make identical soil for ESTD and ISTD test. We are varying the soil components and also varying the soil strains, which will pretty much reproduce the field condition. So we hope that we will still have a universal calibration between these two devices.
Any other questions?
Okay, thank you very much.